This might be one of the world's fastest binary greedy measures. Let's be real, it's probably not, but it's really fast. It is so blazingly fast that it probably puts your culled measure to shame. That's how fast it is. Blazingly fast, Rust and Bevy. Today I'm gonna share with you my journey in making one of the most optimized greedy measures you can probably do. It's going to get technical, we're gonna use bitwise manipulations. It's going to be super interesting, so let's jump right into it. Here we can see my old culled measure. Compare that to my new fancy greedy measure, it generates quite a lot more triangles, as you can see. With the specific shape of terrain, the greedy measure generates about half the vertices. That's great, we use half the data to send to the GPU and half the amount of vertices we need to render. Of course, the less noisy terrain we have, the better the greedy measure can reduce the triangle count, so the benefit varies quite a lot, but overall greedy meshing always produces less vertices, so it's great. There's only one potential problem with greedy meshing though, and that is that it's slower than using a culled measure. Or is it?
Are you sure about that?
Here is a benchmark of my first attempt at a greedy measure. It takes on average 8 milliseconds to create a single chunk mesh. Compare that to my culled measure, it only takes 0.6 milliseconds. Greedy meshing is 13 times slower here. But let's be real for a second, you can probably ship a game with any of these measures. Our meshing needs are highly context dependent. If you're constantly breaking blocks, a culled measure might be preferable. You might take the middle road and implement a simplified greedy measure that is fast but not as space efficient as a full greedy measure. Here's an article of some people using that approach. If you rarely break any blocks, it doesn't actually matter if a greedy measure is slower, so just use a greedy measure in that case. You can also take a hybrid approach and use both of the meshing algorithms to get both speed and the data optimization, but that greatly overcomplicates things and you need to rebuild meshes quite a lot more. It doesn't sound like a good idea to be. Of course, the performance also changes depending on our voxel features. Do you use texturing? Do you bake ambient occlusion? Do you have lighting data? There's not a simple answer to what measure is the best. The only way to find out is to experiment with our specific setup, and that I did. When I first saw my greedy measure performance, I wasn't sure what to think of it. This application I built is very minimal, so we don't know if it's fast enough for our needs. But I saw an opportunity. If the greedy measure is equally fast as a culled measure, we would always use the greedy measure, of course. This was my first attempt at a greedy measure, I'm sure there's space for optimization. So the question is, how much faster can I make this greedy measure? Well, here is the result of me spending a full week optimizing it and managing to make it faster than the culled measure. Yes, I somehow managed to make my greedy measure faster than my culled measure. Now that sounds impossible. It's insanely fast. Now I'm gonna show you exactly how I did it. Buckle up! First of all, we need to understand how greedy meshing works. So let's start with the visual representation. Imagine we are meshing top down one slice of a chunk, just the top part. Let's walk through the algorithm to see how these quads are formed. We start at 0, 0 and we first ask what block type are we working with here, in this case grass. Now we have a 1x1 quad, but we can grow this. So we take a look on the voxel above and check if it's the same voxel type. It's a grass block, they are the same type, so we grow the quad's height. We keep growing vertically until we hit a different block type, in this case we hit an air block. And we cannot grow this quad anymore. We can however grow this horizontally, as you can see. We can only grow horizontally if all the blocks to the right are of the same type. We see that all of the next ones are grass, so that is okay, we can grow it horizontally. But in the next iteration, all of the voxels aren't grass. Our quad cannot grow anymore, so it's done! We then advance to the next location and we're not meshing any air blocks, so we jump up to the next solid block. Then we try to grow that quad using the same method. We have resolved all the y coordinates on the first row, so in the next iteration we jump to the next row and keep trying to go. But as you can see, this block has already been included in the first quad. That is why we have to clear out the data for the quads we have previously meshed. So as the algorithm goes, the data we are working with will eventually clear out. Ta-da! It's a mesh. You can imagine that every step in our algorithm, we are probably indexing into some sort of array that holds our voxel data. Of course, computers are really fast and indexing into an array of hundreds of thousands of times might not be a big deal. But what if I told you we can figure out the height of our quad in a single operation? No jumping around checking voxels every now and then in some sort of loop. We can figure out the height in a single operation. We are going to turn this into a binary problem.
Binary solo.
0 0 0 0 0 0 1.
But first we need to rethink the data structure. Instead of having all of the block types in the same grid, first we'll separate out the different block types into their own grid. All the blocks in this plane is of the grass type, and all of the blocks in this plane is the dirt type. Seeing as we know that all the types in this grid is grass, we can represent the voxel as a boolean. False means there is no grass block. True means there is a grass block. Now better yet, booleans can be represented with a single bit. And you can fit 32 booleans into a single 32-bit integer. Instead of using a two-dimensional array, we now have a flat array, and every single element in our array holds data for the entire row. It looks something like this in code. Now we finally get to see the incredible benefit we get from rethinking the data structure, because we will now figure out the size of the quads using blazingly fast bitwise manipulations. Let's finally take a look at some code! This function returns a vector of quads, and the data we are working with is of course our binary grid plane. We're gonna step through this code and visualize it at the same time. So here we go. We start at the bottom left corner at row 0 and the y0. First we need to find the first voxel that we need to make a quad out of. To do that we need to count all of the error blocks, because there might be error blocks before we reach our first voxel. We will count the trailing zeroed bits. In this example, the first solid block is 3 units up. We count 3 trailing zeroed bits. Now we have our y position. To calculate the height of our quad, well, we count all of the trailing positive bits. It's a single operation, and this function is incredibly fast. So, we now have the height, now we want to grow horizontally. So I construct the mask of the height. I'm not gonna explain this in detail, these are just basic bitwise calculations. If you want, you can pause the video and read my explanation here. So we have a mask of the height, it looks something just like this in binary. So now, we get the same area of bits in the next row. And if all of the bits are the same, that means we can grow into it. As you can see, here's the equal check, and if they're not the same, we want to break out of this loop, and that means this quad is done. But in this case, they are equal, so we continue down into this part of the code. Now it's incredibly important here that we remove all of the bits that we expand into. In this case, these ones turns into zeros. If we don't, the next iterations when we reach this row, we might try to make a quad out of voxels that we have already meshed. That is the entire binary greedy meshing algorithm for a single slice of a chunk, that is. I understand this part can be pretty hard to follow along, but I suspect many people watching this aren't making a greedy measure. But if you are, you should of course visualize this step by step to get a deeper understanding. What is interesting about this code is that we have just figured out all the quads we need, and this function is incredibly fast. Blink and it's done, all thanks to bitwise manipulations. Now let's zoom out a bit. We have only seen how to make a single slice of a chunk. The complete meshing algorithm had to make 32 slices per axis. We make 32 slices facing left, we make 32 slices facing right, so forth. Here's the actual real meshing function that I'm calling. This is a version without ambient occlusion, because that complicates things a little bit in my explanation. Anyway, this function returns a chunk mesh. Chunk mesh is just a list of vertices basically. And as you can see, I have separated out the creation of every single axis. This line creates all the vertices facing up, this line creates all the vertices facing down. If I disable some of these, as you can see, there are gaps in the world now. So what does this function actually do? Vertices from face no AO. Of course we use the binary greedy meshing function we just looked at, but let's jump up to the start of this function. First we loop the axis we traverse, in this case 32 times. I have level of detail implemented here, so some parts of the algorithms use different values, but I won't dive into the details of that here. Here is where I construct the binary grid plane, and of course we make different ones for every block type. We iterate all the values in our binary plane, and we need to fill out the voxel data as binary. So we need to fetch our voxel data. The tricky mind-bending part here is that where we sample our voxel changes depending on what phase direction we are constructing. If we make the up and down phases, of course the axis we traverse is on the y coordinate, but the left and right phases we construct of course traverse on the x-axis. By this point we have the current voxel for the binary grid at this row and this column. But here we also retrieve the voxel from the previous axis. We do not want to make quads for voxels that are inside the chunk. We only want to mesh the face if the current voxel is solid and the previous voxel is air. This is called face culling. If the face isn't culled, we will set the binary grid plane voxel bit to be true. All of this code is just constructing the binary grid plane data, of course using face culling. All that is left to do now is to construct the quads using our blazingly fast greedy measure function. That is the entire greedy meshing function, skipping a little bit of details. And the funny part is, this is the slow greedy measure I showed you at the start, the 8 millisecond per chunk version. The slow part of this algorithm is right here, constructing the binary plane data. We are now going to see how we can make this 40 times faster. And I needed to show you this slow version before I show you the blazingly fast version, because things are about to get a lot more complicated and a lot more faster. Let's think about what we're doing here. Why is this code so slow? Well, first of all, this function is called 6 times for every phase direction. Then we loop 32 times on the axis. We then loop for every single block type. And I only have 3 block types right now, but when we add more block types, the greedy measure will become slower. That's a big problem right there. We then loop the binary grid on the x and y axis 32 times 32 times. And the thing to note inside of this loop, we are sampling voxel data from our chunk 2 times. Let's add the numbers up. In this case, we are sampling our chunk data 1.1 million times for a single mesh. If we had 10 block types instead of 3, we would be sampling voxels almost 4 million times just to create a single mesh. Worst of all, this function doesn't have ambient occlusion implemented, so you can take this number times 27 or so if you're using ambient occlusion. This is the root of the problem, and we can get this number down to 39,000. We will only sample voxel data 1 time per voxel. Technically it's not true, that's the best case scenario, but it is substantially less. And this sampling reduction alone is how we'll get a 40 times faster algorithm. What I'm about to show you is one of the world's fastest binary greedy measures that I'm aware of, so yeah, you know. Here it is! Imagine if I ended the video right there. You know what? Maybe I should have, because this is one of the hardest things in the world to explain simply. I'm gonna try. Here we are, this function constructs a chunk mesh. No surprise there. Our goal is to only sample voxels 1 single time. That's what's going on right here. Interestingly, we aren't sampling 32 by 32 by 32 times. This chunk size includes a padding of 2. That's why I call it chunk size P. It includes a padding. Our algorithm requires adjacent chunk data, because to create the outer face of a chunk we need to ensure that the neighbor outside of our chunk is an air block. That's why we have a padding of 1 on each voxel side. Okay, let's take a look back on the slow measure. The most important knowledge we need from sampling the voxels is what blocks are solid and do they have an air block in the previous axis. We need to know what faces are culled and which are not. These are booleans. Yes, we're going there. Time to rethink this face culling part entirely, so stick with me for a moment as I scramble your mind. Forget about binary and code for a moment. Let's take a breather and go to the drawing board. Imagine we are making this chunk. For simplicity's sake, this is a 4x4 chunk. Now imagine we are constructing the faces looking to the left. Where would the left looking faces be? Well, right here. As you can see, it makes sense. These are the faces looking to the left. Now, the reason we don't make a face here is because it lies outside of our chunk. We still need the neighboring chunk data, but we can only make faces inside of our chunk. Now I want you to visualize where the faces would be that are facing right. I will give you 2 seconds to think. The right looking faces will be right here. Visually, this makes sense. Nothing weird about it. But why? How do we reason about it? Well, this solid block is facing an air block, going back on the axis we are traversing. Same goes over here. This block, however, has a solid touching solid, so we place no face over there. To find our faces, we only care about data lying in the same axis. This is noteworthy. Now let's visualize this as a binary grid once again. We don't care right now what the block type is, we only care if the block is solid or not. Knowing now that face culling only cares about the same axis, we can lay out the binary data like so. This is now a flat array with integers. Now I want to show you how we can find these faces using bitwise manipulations. Let's just focus on this column. Let's do some bitwise operations to see how we can transform this data to find the culled faces. First of all, let's copy this column. Now let's bit shift this to the right. Now let's reverse all the bits. 1s become 0s, 0s becomes 1s. And let's finally add the original row and this modified one together, and this is the result. What does these values mean? Well, if we now overlay this data, you'll notice something interesting. The positive bits indicates where a face would go. Of course, this voxel lies outside of our chunk, so this bit will be ignored in the future. If we want to find the right looking faces, we instead bit shift to the left. Here's what that looks like. We copy the column, bit shift to the left, we flip the bits, and finally add the original with our modified one, and bam, there is our faces looking right. We just calculated where the faces are, just modifying an integer. I encourage you to visualize this with different setups and you'll see it works every single time. We can do face culling incredibly fast. Okay, let's get back to the code. Our goal now is to construct this binary grid I just showed you. As you saw, the faces looking left and right can use the same column data, we just shift them differently. To make the up or down faces, we can use the same axis, and to use the forward and back axis, we can use the same grid. We need to construct 3 different binary grids that we can face cull, and those grids are constructed right here. The tricky part about this code is that I place all the 3 grids in a flat array, so the math is a little bit of a mess. To give you some insight, let me just show you how this data is actually laid out in memory. Chunk size padding times 2 is the amount of elements we need to make a 2D grid. This is a 34 by 34 grid. So to get 3 grids into a flat array, this is the amount of elements we need to skip to jump to the 3 different grids. That's the memory layout. That is why we index differently right here. For the current voxel we are sampling, this voxel has different coordinates on these 3 axes. This is the hardest thing to explain, but I will attempt to. If we construct the binary grid for the up and down faces, of course we are traversing the y-axis. Now the current voxel's x and z position is the row and column, and the y position is the bit location. If we construct the grid for the left and right faces, aka traversing the x-axis, the current voxel's Z and Y position is the row and column, and the X position is the bit location. That is the idea behind this indexing, and this is really hard. Wrapping my mind around all of these coordinates took me a really long time to understand. We can now do our face culling. As you saw previously, we use the same column to calculate both ascending and descending faces. And that is what we're doing right here. Just as I showed you, first we bit shift the column to the right one time, we flip the bits, we then AND it together with the original column. Now we know where every single unculled face is in this chunk. Congratulations, we just went over one of the hardest things in this video, probably. Let's look on some voxels for a moment before we dive back in. Voxels. Our goal now is to find all the unculled faces we just calculated and put them into our binary greedy measure algorithm. We know the locations of the faces, we've been working with binary now, but we need to figure out what greedy plane does this face belong to. Is it a dirt block? Is it a grass block? So let's jump into the code to see how all of this works. So we iterate all the axes, both ascending and descending. Now we iterate 32 by 32 times. The X and Z position here are the coordinates of the binary grid. We get the face called column we just calculated from this X and Z position. And calculating the index for that is not very pretty, you can pause to read my explanation there. Now right here I do some bitwise manipulations to clear the last and first bit of our column, because these bits represents the voxel laying outside of our chunk, the padding. We don't want to make faces out of those. We now have the column data cleaned up, and this is an integer we were working with. We want to find all of the face locations. We already have the X and Z position. What is missing is the Y coordinate, and the Y coordinates of the faces is their bit location. And we can find the first face by calculating the trailing zeroed bits. The Y position of this face is 2. It has 2 trailing zeroed bits. We then clear out this positive bit. These 3 lines will essentially go through all the face locations in this integer. Now we have the X, Y and Z position of the face. To get the true voxel's position, however, we need to transform this data based on the axis we are traversing. We are going to skip this part of the code because it calculates ambient occlusion, which unfortunately is out of the scope of this video, so ignore that for now. Since we now have the true voxel position, we fetch the actual voxel data so we can get the block type, so we can separate out different block types into different binary greedy planes. I actually combined the block type and ambient occlusion as a hash key. Just as you can't merge different block types together, you cannot merge different ambient occlusion values. And here I address a problem with the previous algorithm. Remember how the iteration time increased for every block type we had? Well, instead of iterating all of the block types, instead we get the block type and has it as a key into a hash map. When all the faces are processed and put into the correct greedy plane, we can finally call our binary greedy measure with different block types and different ambient occlusions. Whew. I apologize if I went a little bit faster in the end. I've been working on this video for a really long time, but I hope at least the core ideas about this algorithm has been well presented. Let's do a quick overview here to summarize why this greedy measure is so fast. We sample voxels one time up front, and for every axis the solid blocks get the binary representation. And here is something really cool about this. This code alone takes on average 62% of the execution time. Constructing this vector takes on average 22% of the execution time, and sampling the voxel data into these 3 binary grids take 40% of the execution time. The actual greedy meshing algorithm is faster than just generating the data. How fascinating is that? We calculate all the phases using bitwise manipulations, and look at that execution time, it's not even noticeable that we are calling this. We then extract all the phase locations, we sample our chunk data, 1 additional time for every phase to get the block type. Actually, we sample 9 additional more times per phase if we include ambient occlusion. It's not a huge deal, but maybe there is some potential to optimize the ambient occlusion sampling, I don't know. We finally calculate the quads using this blazingly fast binary greedy measure. I have open sourced this entire voxel engine project. I do not plan to make a public library for this greedy measure because voxel engines are pretty specific in features and data types, and I personally want to use a specific measure designed to run my voxel engine. But the source code is there, and if you want you can extract parts from it. Here are some really cool findings I've made building this. I sent this project to my friend and he ran my benchmarks. He has a way more powerful CPU than me. I think mine is like 15 years old or something like that, and his is just a few years old. But amazingly, the binary greedy measure ran equally fast on my PC as it did on his. But the culled measure, which isn't hyper-optimized code, was faster on his computer. This was confusing. Shouldn't new CPUs generally run code faster? Well, this is the only explanation I've been able to find. It seems like bitwise manipulations and trailing zeros are already so incredibly fast CPU operations that the speed difference in modern CPUs compared to old ones, you won't actually see any big difference in performance. How cool is that? I am justified in using a really old CPU. Hehehe. Wait a minute, pause the video, I just showed you an old benchmark. As I've been updating this function, it's gotten faster, and now there is a slight performance difference in my friend's execution time compared to mine, but still, the difference isn't that big. Why did I improve the code after editing this video? Oh man. Something else interesting to note is that the majority of this algorithm is just doing phase culling. If we remove the last binary greedy meshing part, we can just make a regular culled measure that is incredibly optimized. But why would you do that? Greedy meshing is probably worth it if it is this fast. Finally, I wanna talk about how I learned how to build this, because I haven't found any videos, articles, guides on how this works. Well, I mainly used 2 resources. This video by Davis Morley taught me how binary greedy algorithms works. It is the first resource that greedy meshing finally clicked for me. Now, the binary phase culling I learned from the C++ repository for a binary greedy measure. And I would not have understood anything about this code unless I hadn't made my first slow attempt at a greedy measure. I dissected this code line by line, not understanding everything, but as I visualized things with binary, it finally clicked how all of this comes together. It is not easy to find resources like this on voxel engine development, so I hope this video can be a good resource for other developers wanting to learn how to do binary greedy meshing.
Blazingly fast.
Moldy wantje Hamilton, Sisse Triffio, Tainser Racing, Julian Schmidt, David Klosterman, Pepsi Cora, Turbo Waffle, Gareth, Stefan, Afax, Ingrid, Little,
Patreon.